All right, here's some help with week 7 homework because some of the problems are a little bit crazy. We're going to look at problems 16, 18, 19, and 20. I might work some of these all the way out. Some of them I'll just kind of get you started on. And actually 16 I'm going to skip most of because I think it's similar enough to other ones that you can follow some of the ideas in the other ones. The only thing in 16 that I want to talk about that's not included in the other ones is some review stuff. It asks about vertical asymptotes and horizontal asymptotes, which I don't think it asks for in other problems. Vertical asymptotes are the numbers that you plug in that make the top not be 0, but make the bottom equal 0. But if you look at the numerator here, x squared plus 16, that'll never be equal to 0. Right? X squared is always a positive number. You add 16 to it, there's no way that'll be 0. So there are no vertical asymptotes. Horizontal asymptotes, maybe you remember from the first week of the class, that in the case where the degree of the numerator is the same as the degree of the denominator, they're both 2 in this case, you just look at the coefficients in front of the leading terms. So in this case we have 6 divided by 1. That is, we have a horizontal asymptote at y equals 6. The rest of it I think will be similar enough to other problems that maybe I'll just leave this one up to you, even though I think in office hours I said I'd do this one. Sorry, I lied. But we'll move on to number 17. Number 18. Number 18, we're given this function right here, and we're asked to find pretty much everything about it. Find when it's increasing, decreasing, concave up, concave down, critical points, inflection points. So what you'll end up doing on this one, and really all the other ones too, is you'll have to calculate the derivative, and you'll have to calculate the second derivative. And then we'll do stuff with these. Unfortunately, it's a little bit annoying to calculate these guys. If you look at this, we got a quotient rule going on. So when you use the quotient rule, this comes out kind of messy. So when you try to take a second derivative, it can be kind of messy. So if we get a little clever in how we simplify these guys, maybe they won't be as bad, but maybe that's a reason to do them together. So okay, derivative of this guy. The derivative of the top is 5e to the x. And then we got to multiply that by the bottom. And then from that we subtract, leave the top alone, and multiply that by the derivative of the bottom. And that whole thing is divided by the bottom squared. And this is really a mess. If you try to take a derivative of this, I think you can spend a lot of time trying to figure it out. It'll work, but it'll be really annoying. I think an easier way to do it is to start to simplify this guy. So let's distribute this 5e to the x through. You multiply the 5 and the 5 and you get 25. And then you got e to the x times e to the x. Maybe I do this over here. E to the x times e to the x is equal to e to the x squared, which is equal to e to the 2x. So we'll use this notation here just because I think it's easiest. So e to the x times e to the x gives us e to the 2x. 5e to the x times 3 gives us 15e to the x. And from that we want to subtract 5 times 5 is 25. And again, e to the x times e to the x is e to the 2x. And that's all divided by 5e to the x plus 3 squared. And what ends up being nice is that we got 25 e to the 2x here and minus 25 e to the 2x there. So what happens is that our derivative simplifies to 15 e to the x divided by 5 e to the x plus 3 squared. So when we want to find the second derivative, it'll be a lot easier to look at this guy. Maybe we'll go ahead and do that now. We're going to have quotient rule again, right? Something divided by something. Derivative of the top is 15e to the x. Multiply that by the bottom. 5e to the x plus 3 squared. And from that you want to subtract. Leave the top alone. And multiply by the derivative of the bottom. Be careful here, we got a chain rule going on. Outside function's x squared. Inside function is 5e to the x plus 3. So we got, bring the 2 down, and then multiply by the derivative of the inside here, which might fit. Oh yeah, the derivative of the inside, just 5e to the x. But then don't forget it's the quotient rule, so it's all this mess divided by the bottom squared. 5e to the x plus 3 squared is 5e to the x plus 3 to the 4th. And here's our second derivative. Again, if you try to do anything with this, if you try to set this equal to 0 or set it greater than 0 or less than 0, you might end up having to do a lot of work. I don't want you to get too lost in the algebra, so maybe I'll do it for you. Let's try to simplify this guy. What do we got going on here? We got a 5e to the x plus 3 over here, and down here. So basically what we're going to do is factor out a 5e to the x plus 3 from both of the terms on the top, and then cancel it with one of these on the bottom. That net effect is getting rid of this squared right here, getting rid of this entire term right here, and changing that into a 3. So what we got is 15e to the x times 5e to the x plus 3. And then from that we want to subtract. See, we got 15e to the x, and then we got a 2 and a 5e to the x. So 2 times 5 is 10, times 15 is 150. E to the x times e to the x is e to the 2x. Look good? This is all divided by 5e to the x plus 3, and now we're cubed. Getting better, but we can even do better if we distribute this 15e to the x through. 15 times 5 is 75. 75 e to the 2x plus, let's see, 15e to the x times 3 is 45 e to the x. And then we want to subtract 150 e to the 2x. That mess is all divided by 5e to the x plus 3 cubed. Finally, 75e to the 2x minus 150e to the 2x. Those guys, you can combine like terms and get 45e to the x minus 75e to the 2x divided by 5e to the x plus 3 cubed. And so finally, that's a lot of work, but I think we finally have some stuff we can deal with. We have the first derivative in its simplified form and the second derivative in its simplified form. So from here, you can start to answer all the numerous questions they ask you. Maybe I'll do a couple of them. I think one of them would be something like, when is this guy, I don't know, decreasing? Or actually, sorry, when is f of x decreasing? And the way you have to figure out when f of x is decreasing, it's when f prime of x is less than 0, and f prime of x is this guy right here. So what we want to do is say, okay, 15 e to the x divided by 5 e to the x plus 3 squared is less than 0, and solve for what x's will make this thing here true. You might be able to look at it right now and tell the answer, but in case you can, I'll go a little bit further. The bottom here is always positive. E to the x is always a positive number. Well, really, okay. This is positive, add 3 more, that's positive. Square it, you're definitely positive. So because the bottom's always positive, we can multiply both sides of the equation by what we have on the bottom here, and that will cancel that out and leave us with 15 e to the x is less than 0. So now we're asking the question, when is 15 e to the x less than 0? If you really want, you can divide both sides by 15. When is e to the x less than 0? It turns out e to the x is never less than 0. E is a positive number. A positive number raised up to any exponent is always going to be greater than 0. So this is true always. Therefore, it's decreasing always. Or if you wanted an interval notation, something like that. Maybe from there you can figure out when it's increasing and what the critical points are, but I'll leave that to you. One more thing I'll do on this problem before I leave it alone is let's figure out when f of x is, I don't know, maybe concave up. CC seems like a good abbreviation for concave. A function is concave up if its second derivative is greater than 0. Second derivative is here. So we want to know when is 45 e to the x minus 75 e to the 2x divided by 5 e to the x plus 3 cubed greater than 0. And we can solve that. Again, take advantage of the fact that what's on the bottom here is always a positive number, right? Because it's always a positive number, we can multiply both sides of the equation by that, and it won't change anything. So we got 45 e to the x minus 75 e to the 2x is greater than 0. There's a couple different ways to solve this. Probably what I do is factor out an e to the x, or if you get really clever, you might be able to notice that you can factor out a 15 e to the x. And what that leaves us with is 3 minus 5 e to the x. If you don't believe that step, maybe it's easier to go backwards. If you started here, distribute that 15 e to the x through. 15 e to the x times 3 is 45 e to the x. 15 e to the x times negative 5 e to the x gives you negative 75 e to the 2x. So if you get here, we have something times something is greater than 0. As we discussed, this guy is always positive. So this is greater than 0 if and only if this right here is positive. If 3 minus 5 e to the x is greater than 0. That is, if 3 is greater than 5 e to the x. Maybe I'll move over to here. That is, e to the x is less than, I kind of like having my variable on the left hand side, so I'll move this part over here and divide both sides by 5. And so finally, to solve for x here, take the natural log of both sides, and we get our answer that this function is concave up when x is less than the natural log of 3/5, or in interval notation, everything from negative infinity all the way up to natural log of 3/5. One quick correction here. It looks like I have e to the x is less than 0, and then I said that that always happens. That is not true. E to the x is less than 0, that never happens, right? E to the x is always positive. So e to the x less than 0 is never the case. So the answer here should be never. Let's see, I think maybe WebWork wanted it like this, maybe, just kind of these squiggly brackets with nothing in between them. So in fact, it's never decreasing, it's always increasing. So sorry about that. Everything's still fine, just from this step, the conclusion was wrong.